Welcome back to Everybody Codes 2025. So, for today's problem, we are looking at a group of plants that are in a network graph, and each plant has a thickness and may have one or more branches that also have their own thicknesses. We'll have some free branches and some that are connected to the main part of another plant. Basically, each plant will have a bunch of edges that either are free and are therefore inputs or connect to a plant before them. We see that each plant either has exactly one free branch with thickness 1 or one or more branches connected to other plants. And each branch provides energy equal to its thickness times the brightness energy of the plant to which it's connected. And whenever a free branch is activated, it will provide a brightness energy of 1. Then we also note that if the total incoming energy is less than the thickness of a plant, it does not get activated and so won't glow and won't emit any energy. So it has to meet the minimum thickness. Finally, at the end, we have a single plant that gathers energy from the others, and we want to determine its energy as the output. So looking at this example, when we activate all of the free branches, plants 1, 2, and 3 each emit a brightness of 1. The branch from 1 to 4 has a thickness of 15, so it carries 15 times 1 energy over, and this branch carries 3 energy over, giving a total of 18. Because 18 is at least 17, that means that plant 4 emits an energy of 18. Likewise, plant 5 emits an energy of 24. And finally, plant 6 does not emit any energy because the only branch feeding into it provides 14 energy, which isn't enough to activate it. So when we then go to finally sum, we get 18 times 15 plus 24 times 21 plus the 0 times 34 because plant 6 did not activate, gives us a total of 774. Okay, so to process this input, we'll read the entire input file and split it on double new line. And in each block, we'll have one line representing the plant and a bunch of lines representing the branches. We'll need to store we'll need to store a couple of values. We need the thickness of each plant, which we can store in a dictionary. We'll need the branches connecting each plant to each other, which we'll also store as a dictionary. This dictionary will map from each plant to the branches that go into it, because that's the order in which we'll do our final processing. And then we also need to store the number of plants, which we can just get by taking the length of the plant thickness map later. And the set of plants that have a thickness, that have a free branch going into them. So free branches equals set. Okay. So now initially our plant will be represented as plant X with thickness Y. And so in order to process this input, I'm going to use regular expressions because I find that to be the easiest. So do re.match plant some number of digits with thickness some number of digits, colon. And we'll enforce that that match is actually found to make sure that the string is valid. And then we'll do plant number equals the first group, which are these round brackets basically make the regular expression extract these as groups. And the thickness of the plant is the second group. And so then we'll add that to the thicknesses, and then we'll go to process the branches. So if the branch starts with dash free, then it's a free branch, so we can add the plant number to the set of plants that has a free branch. And I guess we can break here because we're told that each plant either has exactly one free branch or has link branches. Otherwise, we'll again take a match. This time it'll be dash branch to plant group 1 with thickness group 2. And so the plant from which the branch connects, so source plant, is going to be the first match, and the branch thickness is going to be the second match. And so then we'll add that to the link branches. So link branches is going to be a map from each plant to a list of branches feeding into it. So if plant is not in the link branches, we'll set it to a list, and then we'll append a pair consisting of which plant that branch came from and the thickness of the branch. So for example, this will tell us that plant 4 has two branches feeding into it, one from plant 1 with thickness 15 and one from plant 2 with thickness 3, which is what we see in our input. Then let's go to calculate. So we need to get the number of plants. So plant count equals the length of the thicknesses. And then the way I'll do this calculation is basically looping through the plants from smallest to largest, because we observe in the input that each plant only has branches coming in from the plants below it. Um, and so we'll have a dictionary from each plant to its energy. And initially, all of the plants that have a free branch will have an energy of 1. So um, let's loop through from 1 up to the plant count plus 1, because all of our plants are 1 indexed here. So if the plant is in the plants with free branches, then we'll set its energy to 1. And otherwise, we will take the sum of the branches before it. So um, for each branch in the branches linking into it, we'll iterate through that, which is a list of pairs. And the sum is going to be of the energy of the source times the thickness of the branch. And so we'll take that sum and set that to the energy of the plant. Basically, this is saying the energy of a plant with link branches is going to be, for instance, in this case, we loop through each of the link branches, so that will be 1, 15, and 2, 3. And so for each source and each thickness, it'll be the energy of plant 1 times the thickness of the branch, which is 15, plus the energy of plant 2 times the thickness, which is 3. And then if the energy of the plant is less than its thickness, that means that it is not activated, so it will emit an energy of 0. And finally, we just want to get the energy value of the last plant, which is just going to be that of the plant count itself. And so that will get us our answer for part 1. Moving on to part 2, we see that some of the branches have a negative thickness value. These connections have a red glow, and they don't amplify but rather weaken the plant's energy. Taking that into account, instead of activating all of the free branches, we're going to prepare a list of test cases. Each test case tells us which free branches should be activated. We want to calculate the total energy of the last plant across all of these test cases. It tells us to consider only those cases for which the last plant was activated, but that's kind of redundant because if it's not activated, then its energy will be 0. Or, no, I guess it's not redundant because the plant itself would still have an energy even if it's not emitted. Okay. So for part 2, our input processing is going to have to change a bit, but not by too much, fortunately. We now have two sections that are split by triple new lines. So The first section consists of each of the input blocks, and the second section consists of the test cases. The input processing is otherwise the same, and now we need to have a function to calculate the energy of the last plant for any given test case. So let's call the test case activations because it's a list of which ones should be activated. So the activations, I find that the way to make it the easiest is to just pass it to the calculate function as a list of ones and zeros, and then for each index and 1 or 0 in the enumerated values, which pairs up each of these values with its index, um, we'll just do that because the initial energy of each plant with a free branch feeding into it is just going to be whether or not that free branch is activated. Okay, and so in this case, that means that we no longer need this free branches set. Um, and the reason for that is because we can just skip all of the plants with free branches. So I am making a bit of an assumption here, but it's a pretty safe assumption to make based on the description of the problem and the pattern we see here. All of the plants with free branches will be at the start, which means that the first Len activations plants will all be the ones with free branches, so we can just skip past them when processing. So we'll do Len activations plus 1. Um, Technically, this also doesn't account for if one of these starter plants has a thickness of greater than 1, but this again is a case that I'm just going to make the assumption does not exist for the sake of convenience. So what we're doing here is we're initializing the plants with free branches using the activations array, and then we're skipping over them when we go to process, which means that all of the remaining ones will be the ones without free branches. So as a sanity check, let's grab our test case from part 1 and run the calculate function on it with the initial 9 plants all activated. Um, and we see that that gives us the same answer. So we know that this calculate function appears to be working correctly. So going back to this case, now we just need to go through each of the test cases. For each of the test cases, we'll split it on white space and map each of those to an integer. And then we just need to run the calculate function on it. Um, yes, the other thing I forgot to mention is also that because the branches can now have negative thickness, we do need to allow for an optional dash here. So that'll go inside the group because we want it to be included when we parse the thickness to an integer. Um, yes, and of course I also forgot to split the test cases on new lines. Okay, and so that'll get us the energies for each of the test cases, and so we just need to take the sum of that. And that'll get us our answer for part 2. Okay, finally for part 3, this doesn't surprise me that much. The main part of part 3 is basically find the input sequence that corresponds to the maximum output. So, as you may also be able to guess, the input is going to be too large for a brute force. So we're actually going to ignore this test case because this one it doesn't have any particular pattern to it and would just be brute forced. But because we can't afford to brute force here, Um, this trying to solve this test case is not very useful. This is just kind of here for demonstration purposes. So the number of free branches in the actual test case is going to be 81. And I'm not 100% certain that it's going to be that for everyone, but I'm pretty confident that all of the test cases follow the same approximate structure. Um, so 2 to the power of 81, which is the number of cases we'd have to check if we brute forced each plant, each branch on whether or not it's active or not, is a massive number that we cannot possibly check. So that's not going to be how we solve this. Instead, we're going to have to make some observations about the input structure. We notice that there are only 109 plants in total, and 81 of them are input plants. So clearly the inputs are not that tightly connected to the outputs, meaning each input has a limited range of influence on which plants. We'll notice that all of the plants except the first 81 and the last one, or sorry, the last couple, have 9 plants connected to them. And we notice a quite obvious pattern immediately. Plant 82 feeds in from the first 9 plants. Plant 83 connects from the second block of 9 plants. Plant 84 connects with the third block, so on and so forth up until plant number 90. Plant 91 then connects to every ninth plant starting with the first. Plant 92 connects to every ninth plant starting from the second, and so on and so forth. So if we draw this out, we basically have a large grid of plants. And then each row connects to a plant, and each column also connects to a plant, and so on and so forth. Then we see that starting with plant number 100 through to plant number 108, each of those connects to 2 of the plants from the previous layer. And so this will get 82 and 91, which will be the top row and top column plants. So those 2 will go to plant 100. And then the second row and second column will connect to the second in the second last layer. So that's plant 101. And then the third row and column, and then so on and so forth until we get 9 of those. And then finally, we connect all of those together. So this is what that ends up looking like. Basically, we have a grid. We process each row and each column into 18 items in the second layer. So this is the first layer. This is the second layer. Then we pair up the rows and columns into the third layer. And finally, we put them all into the fourth layer. So that's the first observation we're going to make. So this tells us that each of these cells only influences 2 values. That alone doesn't really tell us much because that doesn't actually prevent us from needing to brute force. The second key observation we're going to make is looking at where the negative thicknesses are. All of these values have a positive thickness. Basically, the final layer has all positive weights on the inputs from the second last layer, and then the second last layer also has all positive weights. The second last layer also has all positive weights connecting in from the third last layer. These are all positive. That means that to maximize the last layer, we also want to maximize this. This tells us that we don't need to try to minimize any of these. We can just maximize all of these. And we can also just strictly maximize all of these. Okay. That still doesn't quite get us there yet because maximizing these still would require us to brute force the grid here. So the final observation we'll make took a bit for me to spot. This one is a bit trickier to see. So recall that we said each of the input plants only connects to 2 plants in the second layer. Notice that plant 1 has thickness -4 and -9. Because both of these thicknesses are negative, clearly it should be off for the optimal input. Branch 2 also has a negative thickness in both of its branches, which means that it should also be off. Plant 3 has a positive input to both of its branches, which means that it should be on. Plant 4, plant 5, so on and so forth. We see that each of the input plants is either positively connected to both its row and its column, or it's negatively connected to both its row and its column. Now, I can't be 1,000% sure this is true for everyone, but if it's not true, then I'm pretty sure this problem isn't really solvable. So I imagine this has to be the case since this clearly appears to be the intended solution. What this tells us is for each of the inputs, we can check whether it's positively or negatively connected to its second layer. And if it's positively connected, we want it on. And if it's negatively connected, we want it off. And so that requires no brute forcing. That just lets us derive our answer immediately. And so that's how we'll solve part 3. Okay, so a lot of the code can be shared. We still want to do the parsing the same way. We'll assert that the plant count is equal to. Actually, I'm not going to bother making assertions. Let's just find our optimal answer. Okay. So for the initial activations for the optimal one, we'll start with a grid. We'll start with an array of 81 zeros, and then we'll go through and see which of the plants are positively connected. So for each destination plant in the link branches, for each source and thickness in that branch, and I guess since we don't care about what the destination is, we can just say for branches in link branches.values, for each source and thickness, if the thickness is greater than 0, that means that the source is positively connected. So we'll do activations source minus 1 because of the 1 index offset equals 1. And we'll also check that the source is less than or equal to 81. Basically, what this is saying is for each of the link branches, if the source is in the first 81 plants, which means that it's one of the free branch plants, and the thickness of the branch leading out of that plant is positive, then it is one of these nodes, and so we want it on, so we'll set its activation value to 1. So that'll tell us the input for the best possible score. And so optimal is going to equal calculate of best. And so that tells us that for this input case, the best possible score is going to be 13674. And now we just need to run through all of the test cases. And this time, let's see how they want us to generate the output. We want to compare this ideal score with the result obtained by each of the test cases to see how much they differ from perfection. We only consider the ones who manage to activate the final plant at all. So basically, if the output is 0, we don't take the difference. And so it's the sum of the differences between each test case's output and the optimal score. So the score that it gets is that. And then if the score is non-zero, that means that it activated the final plant. So we'll say print or total plus equals optimal minus score. And so finally, that'll get us our answer for part 3. So very interesting problem. Took me quite a bit to solve it. Once you make the realization of how to do it, the actual implementation isn't too hard. I actually quite like this style of problem, even if I'm not quite as good as at them as I am some other problem types. I think these are interesting because it's not just implementing an algorithm. You have to go through and make observations about the input and try to find the connections that aren't necessarily immediately obvious. So yeah, that's all for today's video. Very fun problem. Hope you learned something and I hope you enjoyed. Thank you very much for watching, and I'll see you tomorrow.